Guys, so day 7, as you can see, this is called types of growth. We're going to basically study the 3 major types of growth that you should be comfortable with at this point. If you haven't seen them quite to this level before, that's okay, but I'm sure a lot of this will look familiar to you. Basically, as anything changes and as you kind of examine the things around you, you're looking at, obviously there's some change going on, but how are they changing? Are they accelerating on the rate, decelerating, staying the same, and so on? So we'll look at the 3 major types that you should be comfortable with moving forward. First one is the most basic. It's just linear growth. As you can see here, it's growing by the same number by adding or subtracting over and over again, and this number is called the slope. If you think about it, if you're growing by the same pace all the time, you just kind of grow like this. It's just level amounts. It's steady. It doesn't accelerate, doesn't decelerate. It just stays even the whole time. Some examples here, obviously you can see in this case the pattern is adding by 2's over and over again, and assuming that pattern holds, that's a linear growth. In this case, this one's subtracting by 5's over and over again, so once again that would be considered linear. The main formats you're going to see linear equations come in, there's basically 3. One of them is called standard form, where basically the x's and y's are all grouped together. That one is probably the least helpful in most ways, but it's fine. Sometimes that's just how it starts. The one you're probably most familiar with is slope-intercept form, mx plus b. That was really convenient for graphing, but sometimes kind of hard to get to if you don't have the graph yet. And then the last one, which you may have seen, or maybe you if you have seen it, may still be a little bit stuck on it, is called point slope form. This one's kind of underrated in my opinion. I actually use that one the most of any of these forms, but a lot of people don't actually get that used to it, and so they think it's kind of weird. We'll see a couple examples down below of what that one looks like and why it's kind of advantageous. So first and foremost, let's just try a couple examples of graphing. I imagine this is pretty straightforward for you. Negative 1/2 x minus 3, so that's in slope-intercept form. And negative 3 is the y-intercept, so we'll start there. The slope is negative 1/2, so down 1 over 2 is usually what you'll see to do. You can also backtrack that slope to reverse the flow, and then overall it should just be this straight line right here. So in slope-intercept form, real easy to use. And number 2, I gave you one in point slope. The trick behind point slope is kind of based on transformations, and so there's some tie-ins there to what we saw with that. Basically, notice that this looks a lot like what you saw with the transformation stuff. The 2 on the outside is going to accelerate it, the minus 4 attached to the x is going to shift this, and then the y plus 1 is also going to be a shift, but directly affecting the y value. If you think about what we saw with transformations, we saw things were backwards when they were grouped with that variable itself. So this is going to move to the right 4, and it's going to move down 1. If you're thinking, wouldn't it be up 1? Isn't the y value normal? Well, if you think about it, bring this over to the other side, and then it's minus 1. So yeah, it actually is down 1. And that's why it's actually not backwards usually, because it's not actually stuck with the y most of the time. Long story short, that means that instead of hitting 0, 0, this line will hit the point 4, 1. And so that can be our starting point. It doesn't have to be on the y-axis. 4, 1 is right here. And then we can use the slope from there to once again generate more points. So the good news is you don't have to know what the y-intercept is to start drawing the line. You really just need to have any point at all. The main advantage to point slope comes in when you have to create a line yourself, because then it's really, really easy. As long as you have a slope and any point, you can make it. Done. And if you have to multiply it out and put it in any other form, you could. So that's lines. I'm sure that's all old news for you. Exponential growth I hope you've seen, but if you haven't, it's basically the same concept but multiplying instead of adding or subtracting. So you're growing by multiplying or dividing the same number. You've probably heard the term exponential growth before, even if you haven't directly studied it. Basically, the graph's accelerating it faster and faster over time. So they aren't straight lines anymore. They do have that feature of getting faster or slower. In this case, we are multiplying by 2's over and over again, so that's what we're looking for there. In this case, we're dividing by 3's over and over again. You could also think of that as multiplying by 1/3, and sometimes that'll actually be an easier way for us to think about those. The graphs of these, as I mentioned, have this kind of increasing or decreasing sort of look to them, and you'll see pretty clearly why that happens. I mean, as we saw with lines, if you're adding the same amount over and over again, there's no curve to it, there's no acceleration or deceleration, it just stays level. In this case, as you notice, these jumps in between the numbers are getting faster. This one only increased by 2, but this one increased by 4. This one increased by 8. So the gaps are growing, and so they're jumping faster and faster and faster. And so you tend to see this sweeping sort of look to it. Usually the format you'll see exponentials come in is something like this, where you might have some multiplier out front, you'll have some base to a power, and then you might have some addition at the back too. This is a lot like what we saw with transformations once again. If you can figure out what the standard exponential model will look like, then the a and the c and whatever else you want to throw in there will make adjustments to it. For two graphs, I'll just make a table so you can kind of see what we're working with here. I'll do a little horizontal table just so I can fit it. And I'll just do -2 to +2. Just kind of a standard amount there. Raising things to a power, I'll start in the middle there. If you raise something to the 0 power, that's equal to 1. If you've never really learned why that's the case, there's a couple of reasons, but for now, just go with it. 2 to the first is just 2, 2 to the second is just 4. If you're a bit rusty on negative powers, don't forget a negative power just makes things into a fraction. So this would be like 1 over 2 to the first, and so that's just a half. And similar thing there with a -2 power, that'd be 1 over 2 squared, which is 1/4. And so what we end up seeing there is, all right, here's 0, 1, here's 1, 2, here's 2, 4. The negatives start getting into fractions, and sure enough, you get a picture a lot like this. Notice it's never quite getting to the x-axis, and if you think about why, look at what's happening with these fractions here. It will get smaller and smaller fractions. -3rd power is 1/8, -4th power is 1/16, and so on. But at no point will you hit 0, and at no point will you go negative. You just get tinier and tinier fractions. So we say we approach 0, but we never quite get there. We just kind of hover right above it. You could hit 0 if you like put a -5 here. That would shift the whole graph down, and then you'll cross 0. But then in that case, you wouldn't cross -5. You'd still have that barrier somewhere. So it all just depends on where you've shifted to. The 1/2 is very similar, and you'll see right away what's going to happen with this one. Let's once again give myself some space here. All right, so -2 and so on. Once again, let's start in the middle. So 0 power is still 1. 1/2 to the first power is a half. 1/2 squared is a fourth. And then if I try to put negative powers on this thing, it's basically just going to have the effect of flipping it back up again. So it's just going to kind of turn back into the way it used to be. This will be a +2, this will be a +4. And if you look at these two tables, they are sort of mirror images of each other. So it's going to look a lot like what number 1 did, but sort of horizontally flipped. I'm going to have a point here, and so on. And same reasoning, it's never quite going to hit 0. It's going to hover right about flat for a while there, and then eventually spike up going into the negatives. All right, so that's exponential growth, and that's based on multiplications. Notice these are 2 to a power and 1/2 to a power. Anytime you have some number raised to an exponential power, that's what's going to happen there. The last one's quadratic, and you've seen this a little bit so far already. The type that we graphed in so far when we used transformations was we graphed in what's called a vertex form. And I actually like that one the best, even though it's not always the one you're going to get. So something like this, you'll see different letters and different whatevers, but something like that is the format that these like to come in. The A is a stretch, the B and C will shift your vertex around, and that's why it's called vertex form. The other kinds that you might see these come in, you might see standard form, ax squared plus bx plus c. That's usually the way that they start, if no one's tampered with it yet. And then finally, you might get it in factored form, or also known as intercept form. And each of these has their pros and cons. The biggest ones that are nice for graphing are this one and this one. We did a lot with this one already. You can use transformations to graph that style. Transformations don't directly help you that much with the other two, unfortunately. And so we'll have to do a little bit of other stuff to get there. But let's try the examples. X squared, I guess, is so obvious we can just jump right into it. 0, 0, 1, 1, 2, 4, and so on. And so we end up getting, I'll do 3, 9 as well. Oops. And so we end up getting that standard U shape. Now, there's no stretch here, so it's going to grow the way it normally does. In number 2, again, this is not in vertex form. This is not in the transformation form that we did. So using the shifting and the stretching won't really help that much here. Instead, I'm just going to try to factor this. And it turns out this does factor nicely. If it doesn't factor nicely, you're down to doing some other techniques, but this one did, so I'm just going to go with it. Given those factors, if you think about how solving works and so on, which we'll get into more later, there's two values here that should kind of pop out at you. X equals +4 and x equals -2 should be moments where this thing hits 0. And so as we think about that, that means there's points at 4 and points at -2 on the x-axis. Just knowing that alone is actually enough that we can kind of reverse engineer what must have happened here. Because if you look at the shape of this thing, with just the standard shape, it's centered all the way through. So if we kind of draw that center line there, we notice that these 2 points are each 1 space apart. These 2 points are each 2 spaces apart from that center line. That's also known as the axis of symmetry, which you may talk about. So that means that if these two are 6 apart, 3 and 3 right in between them, there should be the vertex point somewhere along that line. And we also know this thing wasn't stretched at all. There's no number out here stretching it, so it should have the standard growth. It should grow 1, 1, 2, 4, and so on. If we kind of put all that together and think backwards, we'll realize this must be dipping down to 9 because of the spacing of these 3's here. Let's put it all together and show that. So from this vertex, it would grow 1, 1, it would grow 2, 4, it should go 3, 9, and there we go. We're hitting that point right there. There's more to it than that. You can graph this any number of different ways, but that's just one way to kind of logic your way to the answer, given what we know so far. Okay, and that's parabolas. So the last thing is, given just a list of numbers, basically a pattern, can you figure out, are they growing linearly, quadratically, exponentially, or are they just going some other way? Something to point out, if you look at the way a parabola grows, oftentimes I hear people say, oh look, it's growing exponentially, it's getting faster. It is getting faster, but it's not growing exponentially. Exponential is something different. That means that you're multiplying repeatedly. And if you try it, you'll find that that's actually not how these are growing. Their growth is not based on multiplication, it's based on squared numbers. We'll see in a moment what else is going on there as well. All right, so first things first, how is this one changing? Hopefully right off the bat you can notice subtracting by 3, this means it is a linear type of growth. And it says if you can, try to write a formula for each pattern as well. So I'm going to go ahead and say that this was the point when you plugged in 1. That's usually what you're going to say. So when x equaled 1, the answer was 7. When x equaled 2, the answer was 4. With linear patterns, this constant change is the slope. That's what it keeps changing by. So right off the bat, we know it's definitely a negative 3x. The question is, what's the number that sits next to that to make it all work out? And if I put a plus 10 here, then when I plug in 1, I'll get negative 7, and so on. So that kind of calibrates it to be the right numbers. All right. Number 2, you might recognize these numbers, 100, 9, or 81. This is 10 squared, this is 9 squared, this is 8 squared. So these are squared numbers, so right off the bat, that gives it away that it is a quadratic. Now, it's not always that obvious. So let's think about something else you might notice here. If you look at the change, this one went down by 19. This one went down by, let's see, what was that, 17. This one went down by 15. And so they're changing by odd numbers. The other thing to notice is if I now look at those red values and notice their gaps, this is changing by 2's. The amount of change is changing by a consistent amount. This is what's called the second difference. And when that is consistent, that means it must be something quadratic. It's not always obvious what it is. You'll see one in the practice problems that is, you can tell it's quadratic if you try this pattern, but it's very difficult to come up with a formula for it. So you'll see in the key, I put it there. Feel free to mess around and see if you can solve it yourself. But you can at least verify that it is something quadratic. Now in this case, to make this do 10 squared, 9 squared, 8 squared, and so on, you could do something like this, and that would get the job done. Play around with that if you need to see where I'm getting that from. Okay, next one here, we can find off right off the bat here, this is multiplying by 2's, so this is exponential. And there's a number of ways you could do this, but the easiest way in my book is start with the 3, and then the thing that's raised to a power has to be whatever keeps happening, in this case the 2. That shouldn't be too surprising if you think about how the slope worked, but it really is just based on the fact that you keep multiplying by 2's, and 2 to a power will, sure enough, make multiplication by 2. Now, this is not quite right yet, because if I plug 1 into this, I will get 6, so I'm off by a little bit. One of the easiest tricks is just to put a -1 there, so that you kind of offset yourself by that amount. When I plug in 1, I'll get 3. When I plug in 2, I'll get 6, and so on. That kind of recalibrates the spacing there. All right, last one here is probably the trickiest one, and it's not immediately obvious what's going on here. If you check for addition, let's try it. This is plus 16. This one is plus, let's see, what's that, 24. This one is plus 36, maybe? Something like that, yeah. So it's not linear, so it's adding by different amounts. So cross linear off your list. If you look at the second differences, all right, so this one increased by 8, then this one increased by 12. All right, so it's not quadratic. Oops. So that one failed also. That means that it's either exponential or it's just not one of the patterns that we've just talked about. Let's try exponential and see. Now, here's the tricky part. You don't want to just have to guess and check. We could tell this one was doubling. That was pretty obvious. But it's a little bit trickier to just guess what number this is changing by unless you are pretty good with your number sense. An easier way is to think about this. All right, so 32. If this is exponential, then there must have been some mystery number that I multiplied by to make 48. If it's exponential, it's got to fit that situation. Well, you can use basic algebra to solve this. And if you divide by both sides, you'll end up with that question mark being 1.5 or 3 halves. So if this is exponential, that's the number. Try it, check it. Does 48 times 3 halves equal 72? It turns out it does, and this ends up holding after all. So if you can't find the number, just solve for it. Just figure out what it must be. And again, if that hadn't worked, we would just say it's none of these things. We would just say it's some other pattern, I guess. All right, putting it all together here, this is exponential. Putting it all together, we have 32. The common change is 3 halves. And if we use that -1 trick, that'll calibrate things to start in the right place. One final question. A little bit of a story problem here. So Jeremy gets a new job, starting with a base salary of $45,000, and then each year gets a 3% raise. How would that grow over time? So what type of growth? If you're getting percentage raises, that means if you think about how percentages work, you're multiplying by a percent every year. That by very definition would be something exponential. And if you need to play around with the numbers, go ahead and do so. An equation for this is actually not too hard to do. I think most people, just based on, without thinking too hard, would probably say, oh, 3% is this, and be done with it. There's a slight problem with that. If you try this, you're going to find this will only compute the amount of increase. It won't actually compute as actual new amount. If you put an extra little 1 right here, suddenly it'll all work out. And basically the thing behind that is you still want 100% of your old salary. You just want 3% more than that. And 103% is 1.03 when you change it into a decimal. So that should work out. Now, just like before, we got to check and make sure we land at the right place here. We do once again want the -1 there so that year 1 is still 45,000. Okay, so at this point, try the practice problems. See which ones you can figure out. Some of these types that you'll see are kind of tricky, but once again, look at them, try the answer key, and see what works, and we'll go from there.